Yo, and welcome. This lesson is going to be on inverse functions. We're starting right from the scratch of inverse functions so if you don't know much about inverse functions or you've never even heard of an inverse before, this is the correct lesson for you. Alright, so firstly, what is the notation we use for inverse functions? So if f of x is a function, then f to the minus x is its inverse. And just to be really clear, this is different from the reciprocal, right? 1 on f of x. In mathematics, the way we would write the reciprocal, normally, if it's 1 over, it has a minus 1 to the power. But if you write it the normal way like this, it just looks like the inverse. So we differentiate it. So for the reciprocals, we would write it like that. So that's the reciprocal of f of x, where right here is the way we'd write the inverse of f of x. All right, so what is an inverse function? So a function and its inverse are like opposites. So the idea is one of the functions will undo the other. And it can work either way. The inverse will undo the normal function, or the normal function can undo the inverse. Let's have a look at an example of that. Here I've written down two inverse functions. The one in blue, f of x, which is the function is x cubed, and this orange function, g of x, which is the cube root of x. Now we're about to learn in a couple moments how to find the inverse of a function, so you would be able to test to show that these actually are inverses, but for the moment, just believe me, these are two inverse functions. If we sub in a value x equals 2, so right here, let's just plug in the value x equals 2 into f of x. So f of 2 will end up being 2 cubed, which gives you 8. Now, if you sub that value 8 into g of x, g of 8, you end up with the cube root of 8. It gets you back to 2. So what ended up happening here was f of x turns the 2 into an 8. And then you plug that 8 back into the g undid what f of x did. It turns the 8 back into the original 2. So this is an example of two inverse functions undoing each other. And as I mentioned earlier, it happens vice versa. It can work the other way. G of x can just as easily undo f of x, right? They're opposites of each other, so it doesn't matter which way you do it. In this case, let's stick with the value 2. If we were to instead plug 2 into g of x first, you'd end up with a cube root of 2, which I'd personally just leave it as an exact value. But, if you wanted to know what that was as a decimal, it's approximately that. If you plug that value into f of x, of course, you'd end up with that cube root of 2 cubed. It ends up undoing everything g of x did and gets you back to the value 2. So inverse functions undo each other and just return you with the original inputted value. All right, or more formally, if you write them as composites, they completely break each other down and just leave you with that x there. And here you can see in the first composite function, we have f of g of x. So that is, f of x was x cubed, g of x was the cube root of x. So f of g of x, this basically means you've got this f function, and we're replacing x with g of x. So you start writing out the f of x function, but that x there needs to be replaced with g of x, which is where the cube root of x comes in. And of course, cube root and the cube cancel each other, leaving you with an x. And if you look back down to the other one, you could have, of course, written it the other way, g of f of x, and the same sort of thing. You rewrite g of x, but replace x with the f of x function. They end up undoing each other, returning you back with the x. Right, so So in this case, we can see that the function and its inverse do end up undoing each other. I do just want to illustrate a super crucial point at this moment. Get rid of all this sort of stuff here. Oh, by the way, I should also mention, if at any point you want to pause the video to copy down notes or any examples, of course you're free to do so. You know, take whatever you can out of this video. What I want to mention though is here we had the cube root and the cubed cancelling out each other, just leaving you with the x. This is not the case for the square root and the square. If you had these other functions, x squared, and this other function g of x, which is the square root of x, I can tell you now, these are not actually inverse functions. They could be if you restricted the domain, but as they stand, they are not inverse functions. And you guys know, when you go ahead and evaluate g of f of x, you'd end up with the square root of x squared, and you know that is not x, right? That's the algebraic definition of the absolute value of x. So just to mention, these are not inverse functions, and we're actually going to look in more detail towards the end of this lesson, which will hopefully only be in about 10 minutes time, about why this is not, so you won't get caught out by these sorts of little tricky traps that can occur with inverse functions. All right, so how do we find the inverse function? All right, so this is, I guess, probably the main, most crucial skill in terms of you getting marks. How do we find the inverse function? Well, nice and simple. You swap your x and y pronumerals around, or f of x, and then you then rearrange it to get y back by itself. In other words, make the y the subject. For example, let's find the inverse function of, well, there's a couple of them to do. Here's our first one. F of x is x plus 2. So first step, we're just going to swap the x and y's around. I know there's an f of x there, but I'm just going to rewrite it as a y, just because it's a little bit easier, like less messy. Okay, so I'm going to replace the f of x and the x. I'm going to swap them around. There it is. I've successfully swapped the x and y pronumerals around. The final step is just to rearrange and make y the subject. Nice and easy. Take that positive 2 across to the other side. There it is. Y is equal to x minus 2. This is our inverse function. And then I'll probably just rewrite it at the end, as our inverse function is x minus 2. That's it. So you swap x and y around and then just rearrange. That's how you find an inverse function. So f of x was x plus 2. The inverse of f was x minus 2. They're like opposite functions. Let's actually test them to make sure they actually are inverse functions. So let's work out, what is f of minus 1x. Let's find that composite. Do these two functions actually undo each other? Well, let's check it out. Right? F of x is x plus 2, but f of minus x, we have to replace this x with, here it is, inverse x. And when we do that, here we see we just end up with x. They ended up undoing each other. Again, so if you're not super familiar with finding these composite functions, right, we've got the f function here. And our goal was, normally it is f of x, right? But that x has been replaced with an f to the minus 1x. So when we rewrite that f function, here it is, we need to replace the x with the other function. And here we can see these actually were inverse functions. They undid each other and gave you the x. If you wanted to, you could test it the other way. It's just as easy, and they'll undo each other and you end up with the x. All right, second example, let's find the inverse function of now an exponential. Okay, so this one here is pretty super fun. I'm not going to lie. You need to have some knowledge of exponentials and logarithms to do this one. So hopefully you're in that situation. So first step, we're going to replace the x and y. Where there was the y or f of x, I replace it with the a. You know what to do. We've replaced them. Now we need to rearrange this to get y by itself. Y is up as a power. We need to try and get that y down so we can then rearrange and make it the subject. The only way we're going to be able to get a power down is to use our logarithms. So I'm going to log both sides. I'm going to do it to the base 2. It's not super necessary, but it will make our answer a little bit more simple, like simplified. So I'm going to log both sides and take it to the log base 2. That then allows us to use our log laws and take this y down the front. And you may know that log 2 of 2 is actually equal to the value 1. Okay? So, and the idea behind that is, your base is 2 to the power of what is equal to 2, and it's 1. So we actually end up with here, we've actually got it, because log 2 of 2 is 1. So y is equal to log to the base 2x. We've found our inverse, as easy as that. There it is. So we replaced the x and y, we rearranged to get y by itself. So, and I should probably rewrite it now, because the question didn't originally have y, right? We created that. So I should probably rewrite it using inverse notation. F to the minus 1x is equal to log 2x, right? So the inverse of 2 to the x is log 2 to the x. Does it work? Again, you don't necessarily need to test it, but I am going to do that here for you guys, just so you can see. So if f of x is 2 to the x, the inverse function is log 2 to the x. Let's see if these functions actually do undo each other. This time I'll rewrite it the other way. I'll do the inverse of f of x. Let's see what this ends up giving us. I'll do it below because I'm going to run out of room across there. All right, so I'm going to rewrite the inverse function, which is log to the 2, replacing x with, the normal function, which is 2 to the x. Here we can see that x can come down the front, leaving us with log 2 of 2, which we've already established as 1. We end up getting x. Look at that. Hooray, it worked. So again, here it is. We've found the inverse function, and they do happen to undo each other. They really genuinely are inverse functions. All right, third example. Now let's look at a hyperbola. Right, this will be super tricky, right? Same thing. Replace this is our y, this is our x. Replace your x and y, and then just rearrange. I'm going to take the y minus 2 across to the other side. Maybe now take the x across. And here we can get y by itself pretty easy. It's just 1 on x plus 2. So the inverse to this hyperbola, 1 on x minus 2, just happened to be another hyperbola. Similar but different. So that's how we find the inverse function. And again, you could test it if you wanted. By doing that composite, it'll end up working. Or you could just plug in a random value, right? As long as it's not the value 2 or 0. I should say, because there are some domain restrictions that are going to be happening with the function and its inverse. On to the fourth example. Okay, so this is a harder hyperbola. So let's find the inverse function of this one. Here it is, the start of it. Oop. Okay, so I've replaced our x's and y's. Now we need to sort of just algebraically get y by itself. So let's take this across to the other side. There's a couple different ways to do this, to be honest. My inclination would have been to originally simplify this right-hand side, but let's pretend I didn't see that and I just go ahead with this method. We end up getting this. I'm trying to get y by itself. Let's collect these y's. I'm going to take this y across. So I've got y outside of x minus 1. I've taken that y across to the other side and factorized it. And I'll take this minus 2x over to this side. So I end up getting this. And there we go. Minus 2x plus 3 all over x minus 1. That there, and of course I'm going to bring it up here and rewrite it. This here is the inverse function. That's a minus 2x plus 3 all over x minus 1. That can be simplified, which is what you would need to do to get, I guess, the other expression if I simplified it first and then went ahead and did it. But there, that is the inverse function. You know, you've answered the question. For those that are curious about how to maybe do this and get it looking a little bit nicer straight away, that original, so once we've swapped the x and y's around, I personally would, use that old trick of, hey, x plus 3 is x plus 2 plus another 1. And so now I'm going to be dividing these things by y plus 2. So y plus 2 divided by y plus 2 just gives you 1 whole. And then you're left with this 1 over y plus 2 at the end, which, may or may not, I don't know, maybe it's not necessarily any easier. But, rearranging, I'm going to flip both sides now. And then bring this up here. Y will end up being 1 over x minus 1. Take away 2. This certainly would be much easier to sketch. Well, this would be our inverse function. But it may not look like it, but this function here that we have is exactly the same as this one here if you chose to simplify the one up the top here. And how would you do that? Ultimately, you'd have it as a minus 2. What do you have to do? Maybe a plus 5. Which would allow you to factorize this top part here and then cancel down. It'll end up getting you the same answer. So anyway, so that's how we find the inverse functions, right? So do all functions have an inverse? Well, the answer is no. Only one-to-one functions do. That is, for a function to be one-to-one, it also needs to pass the horizontal line tests. So if you have a particular function, and this is a function, right? X squared plus 6x plus 10, it passes the vertical line test. We have a function here. Does it have an inverse? As it currently stands, no. We would actually need to restrict the domain of it. Let's have a look at what it is I am talking about. So firstly, let's go ahead and sketch this thing. Let's be honest, it's one of the, I would be completing the square. Well, that's the way we would do this, right? It can't factorize. You can't find your x-intercepts. We know what the y-intercept is. That's 10. Has no x-intercepts. Complete the square. You end up with x plus 3 all squared plus 1. If you're not sure how to do that, definitely get your algebra skills up to scratch. Let me know and I can make a video if you want. All right, so you end up with this function, which is, I should say, is hyperbola, which is going to be at -3. All right, and this is going to be the value of our 1, it seems. All right, so this is where the function exists, and here you can see it straight up fails the horizontal line test. I can quite simply draw a horizontal line right there, and it hits the function at 2 separate points, meaning this won't have a inverse function as it currently stands. And if we were to go ahead and actually try and find the inverse function, that's exactly what will happen, right? Whether you plug it into the original function or this completed the square function, let's go ahead and do it. Let's replace x and y, and then just rearrange to get y by itself. So you end up with y plus 3 is going to be equal to x minus 1. I've just taken that positive 1 to the other side. By the way, I rewrote the two sides the other way around to get y on the left-hand side, just because I'm more comfortable with it. The next step is going to be to square root, giving you a plus or minus the square root of x take away 1. This obviously is the issue here, right? There's 2 separate inverse functions. We go ahead, we find what y, it's a -3 plus or minus the square root of x take away 1. So in other words, our inverse function isn't a function, there's actually 2 separate ones. So in this case, we were able to find expressions for the inverse, but they're not actually, like there's 2 separate different ones. And ultimately, where those 2 different ones have come from the idea of the only way this could be and this function could have an inverse is if you broke up the domain. You cut it off at this point. So if you just looked at, let me pick a new color here. If you just looked at this right-hand side, that function there, if you put the restriction on the domain, that does have an inverse function. And it would end up being the positive equation down here, the one with the positive square root of x minus 1. And, likewise, where I'm going here with the other one. Let's pick the color yellow. And, of course, if you broke off the domain, that does not work. That didn't. Purple and yellow together. This will probably look nice, maybe. Okay, if you broke the domain and just looked at, x is less than or equal to -3, if you use that domain, then that left-hand side, the purple and yellow section, would actually have a inverse function, and it would be the negative version of that equation we found at the bottom. So, final aspect of inverse functions that we need is the geometric properties. A function and its inverse will be symmetrical about the line y equals x. And what we're going to do is we'll have a look at some of these examples that we've already done and just show you exactly how that works. So if we look at this function here, which didn't originally have an inverse, but let's say we did just restrict the domain to consider the function x squared plus 6x plus 10, where x is greater than or equal to 3. Right, so in this particular case, this would have an inverse function. It would be, let me go down here and just erase that negative. That is the inverse of it, right? What would it actually look like, right? We're exploring the geometric properties here. Well, let's put in this line y equals x. The inverse function, -3 plus the square root of x minus 1, would actually be a graph that looks like this. it would be perfectly symmetrical. And when I say perfect, I mean like more perfect than what I've done. It would be something that's completely symmetrical to the original function about the line y equals x. And for those people that are familiar with, you know, your square root graphs, the moment you have a square root of x minus 1, you would not be surprised at all that our graph started at the value 1, right? Because when you're taking the square root, you can only square root positive values. X minus 1 needs to be greater than or equal to 0, which means x needed to be greater than or equal to 1. So I've just geometrically, without any knowledge of this, I've just copied what was on the other side of y equals x, and my graph just randomly started at this value 1. Algebraically, we can see why that actually occurred. This inverse function down here only does exist for values greater than or equal to 1. What about some of these other inverse functions we've done? That's too messy. What about this one here? If we wanted to find, look at the idea of these things being symmetrical about the line y equals x, well, what would this original function look like? 1 over x minus 2, it has a vertical asymptote at the value 2. There it is. And it's a positive hyperbola. That means the original function, which I'll do in blue, just so we can keep the function and the graph the same color, looked like this. Here and down here. By the way, you can see why this function here did have an inverse, right? It passes the horizontal line test. You can't draw a horizontal line at any point that hits this function more than once. And its inverse function, which we did find, it was 1 on x plus 2. So let's go ahead and graph that. So 1 on x plus 2. So this has a vertical asymptote at 0. And it has a horizontal asymptote of 2. I know these asymptotes are getting a little messy, but I'm comfortably ignoring the purple. All right. So we ended up with a function like this, and the other one was here. It's a bit hard to see. It's easier to see with the positive version. I think my graph isn't maybe the best, but if we highlight this positive version, you should be able to hopefully accurately see. If I get rid of all the rest of this garbage, hopefully you'll be able to see about this line y equals x. Look at the symmetry that's occurring with the two graphs. Okay, as if I was to extend them more, you see they've got this perfect symmetry about the line y equals x, and that will go through right through all of them. So sometimes you're not given the function, like what the equation of the function is. You're just given a graph and they ask you to draw, or it might be a multiple choice question where they give you 4 different graphs and they say which graph is going to be the inverse of this. And again, that's when, if you don't have any of the actual functions in front of you, you'll need to use this geometric property. They will be symmetrical about the line y equals x. Anyway, hopefully this helped. If you have any questions, just leave any comments either on YouTube or back on Canvas, and I'll see you next time.